Here we have a solid metal sphere, and the radius is given by the capital R. This capital R is equals to 3.00 meter, and this metal sphere have a charge Q minus 5.50 microcoulombs, and we write down the general solution. This the Gauss law. Closed loop integral E dot dA equals to the Q enclosed over the epsilon naught. From here we know this is E and 4 pi r squared. This is equals to Q enclosed over the epsilon naught. So E is equals to the Q enclosed over 4 pi epsilon naught r squared. Now we start with the first one. He asks about the magnitude of the electric field at the distance 0.250 meter, and this is less than r. We know this is the solid metal sphere. That means in equilibrium the charge will located at the surface here, and the inside the electric field is equals to 0. From this Gauss law, we know this for case A, Q enclosed is equals to 0. So the E will also equals to 0. This is the answer for A. Now B, the same reason. This is 2.90 meter, also less than R. Same reason as the A. The enclosed charge is equals to 0, so the electric field also equals to 0. Now C, we have 3.10 meter, and this is greater than R. Now here we apply this formula. The enclosed charge is just equals to Q, and now we calculate the magnitude. R, this is 3.10 square. Here I get this is the 5146 Newton coulombs, and if we only want the magnitude, we can put this thing, so the negative we don't need to consider and answer. Now D is 8.00 meter. Now basically same as this C, just the R is different. Mm-hmm. 8.00 square. So here I get 773 Newton per coulombs. Now E, uh, how would the answer differ is if this sphere were a thin shell. So mm, in the thin shell case, it's basically will produce the same result because you can see if this thing is a solid metal, right? All the charge will uh, go to the surface, and the electric field inside is basically zero. It say this is a solid sphere. Now, another case here, we just have a thin shell inside a. This is not the solid inside; is the empty, but still the same thing. The charge will locate all around this surface. So by the Gauss law here, we basically will get the same answer. So we can write this is no different for a thin metal shell. Uh, Now we finally go to the F. A solid non-conductor uniformly charged throughout. So actually this will give us the different result because this is a non-conductor and the charge are not free to move. So here we have a non-conductor and this is basically the charge is distributed equally. Now if we apply the same thing, the Gauss law, this is a Q enclosed over the epsilon naught. This is E and 4 pi r squared. This is Q enclosed over epsilon naught. Now here we will make the difference is that the charge enclosed, even you take the radius is less than this capital R. This is capital R, and even you take a radius they are less than this capital R, we still have the charge that enclosed in the area we define. So we can write this is E equals to Q enclosed over 4 pi epsilon naught r squared. Now, one thing we know is the charge density. The charge density will always remain constant, right? Because this charge is distributed uniformly. So the charge density is given by Q over the V, right? From here, this rho will equals to Q enclosed over the volume we define, and also equals to the Q over the volume of this sphere, and this Q is a total charge. This is for the case where R is less than the capital R. Mm, Now we know this Q enclosed. The volume defined is 4.3 pi R cube equals to Q over 4.3 pi capital R cube. If you can see, this can be cancelled. The Q enclosed well equals to Q uh, R cube per capital R cube. So we substitute back into this formula. This is what we will get. This uh, Q R cube per capital R cube, and this is a 4 pi epsilon naught and R square, and this R square will get cancelled out. So the final result we get Q 4 pi epsilon naught R cube, and whole thing multiply with this R. For this, we have this expression. We can recalculate the case for this A and B in for this uniformly distributed charge in a non-conductor. So let's do it. First, we remember the R for the A is 0.250. This is equals to this is the charge. We take the magnitude, and 4 pi epsilon 8.85 10 to the negative 12, and this capital R is 3.0, the radius of the whole non-conducting sphere, and we have to multiply with this small r, 0.250. This is equals to 457.9 Newton per coulombs. Now same thing for the B. In these two cases is this R is less than this capital R. So here I get this is a 5312 Newton per coulombs, and now for this C and D, this R is greater than capital R. We just uh, apply this uh, formula here, the same thing, but now the charge enclosed will just equals to the total charge. We enclose all the charge. I think let's put this for the magnitude. So this is 3.10. Mm, oh, 3.10. I get this is 5,146 Newton per coulombs, and this 8.0 for the case D. Mm, 8.0. Here I get this is 772 Newton per coulombs. So all this R is in unit of a meter. I think I better write it down. R in units meter. So here is the answer for this question. And you can see these two for this case C and this D, right? C and D. You can see we get the same answer for this C and D, but this will be different case for the A and B. Here you can see after this the R is greater than this capital R, you will get the same answer for both case. This conductor or non-conductor, that the charge is distributed uniformly. Since this Q is negative or electric uh, field line is point toward the sphere.